Okay, super short section today. So, chapter 1 still. Alright, we really only have one single definition in this section, so here it is. If we start with two congruence classes, A and B, then we can define addition and multiplication in the only way you can probably think of. Simply take the two representatives and add them, or take the two representatives and multiply them. Now, this is the first time, probably, in math where you have to check that something's well defined, because it looks like a reasonable definition, but it could actually be nonsense. And that's because in my definition, I chose the representatives, A and B, and used them to define addition, A plus B. But a priori, that same congruence class can be represented with different representatives, and maybe if I picked a different representative, I would get a different answer. For example, let's work mod 12 here. So by our definition here, the congruence class of 3 and the congruence class of 6 is defined to be the congruence class of 3 plus 6, which just means 9. Now, we can also write this congruence class for 3 in different ways. For example, 3 is the same as 15, because they differ by 12. But if I take 15, its congruence class, and add it to 6, I get 21. Now, if my definition were well defined, then this ought to be the same as this. And here, if you look at the difference, indeed, they are the same, since they differ by 12, I guess. Anyway, you can see that the answer looks at first as if it might be different. So we're going to check that these two definitions are well defined. All right, so the claim is it's well defined, meaning it doesn't matter which representatives we choose. So here's the setup. If we have two congruence classes, and they can be represented by different representatives, so A1 is equal to A2 and B1 is equal to B2, then we want to show that the sum is independent of which representative we chose. In other words, we want to show that. So we want to show that A1 plus B1, its congruence class, is the same as A2 plus B2. This is, of course, equivalent to showing that A1 plus B1 is congruent to A2 plus B2 mod n when A1 is congruent to A2 and B1 is congruent to B2. But this was exactly what we checked back in Lemma 116. So that's it. The argument for multiplication is exactly the same, and that'll finish the section.